Hello everyone, welcome to another video on molecule simulation using Gaussian software package. In the last videos, we have seen how to optimize a carbon dioxide structure using Gaussian software, and today I will show you how to optimize and analyze the thermodynamic properties. And to do this, I have to first open the file, optimized file. This is the output file we have got from the geometric optimization. Now I will just optimize it again in frequency mode. Here I will select frequency, and additional keyword GF input is already here. These options will remain unchanged. These are also okay. Here I will give the memory limit 1500 megabyte, share process 4. Rest of the things will remain the same. Now I have to submit. I'm just rename this file, and then we will optimize it as procedure we have learned for the geometric optimization. Yes, the Gaussian job has completed. This optimization will also give you three outputs like before. One is input file, which we have chosen here, given as input. The other two file is the chk file and the log file. Here is the optimized output. You can see that here. From this optimized output file in the frequency module, you will get some informations. Obviously, you will get the thermodynamic informations, but before going to the thermodynamic analysis, I just want to show you another important thing, which you will find from result and vibrations. This is basically, we call it IR spectroscopy analysis, and this part is required for that type of analysis. When someone is analyzing IR spectroscopy, it means he is trying to establish this thing that the bonds are formed properly, and uh, using this higher frequency we can show different characteristic bonds as well as different characteristics vibrations present in a molecule. And sometimes the infrared values can come in the negative frequencies or imaginary frequency. If you get any infrared peak in the value of negative frequencies, then it means the structure will not form at their true energy minima. Or, in other words, I can say that the structure will not be formed at their ground state at room temperature, because these calculations are basically made considering the room temperature. But if the negative peak arises, then it will surely explain that within this criteria or in room temperature, this structure is not possible to be formed. And that's the significance. So you can also check the animations of the vibration from here. I'm just showing you. You will just click start animation. You can see, okay, you can clearly see the bending of carbon dioxide. And these are the things you will get. Now I will straight dive into the analysis of thermodynamic properties. Okay. So to analyze thermodynamic properties, you have to go to this output file, log file, and you can just search Gibbs here. Okay. Basically under the thermochemistry value. Okay. I just search with the keyword Gibbs so that I can found it directly. Okay. So these are the optimized value, or these are the values of Gibbs free energy, enthalpy, and entropy, the major thermodynamic properties which we generally use in different papers to understand the thermodynamic behavior. And here the thermal free energy, the sum of electronic and thermal free energy, is the Gibbs free energy, in other words. And these sum of electronic and thermal enthalpies are basically enthalpy. Okay, so these are the things we will get from here. Okay, and to find the entropy, we can just subtract the Gibbs free energy from the value of enthalpy and then divide it by room temperature, as all the calculations are made in the room temperature. That's why. And also, oh, I forgot to mention that these values are obtained in Hartree value. To convert a value from Hartree to electron volt, you have to multiply the value by 27.2114. That's it. So in this way, we can analyze the thermodynamic properties. And that's all for this video. Okay, see you soon.